In this video, I would like to share with you an effective method of proof known as the extreme principle, which will enhance your ability to construct a mathematical proof. You will also learn to distinguish this method from the most notorious and more frequently employed method by contradiction. Consider a network of finitely many balls, some which are joined to one another by segments. We shall color the balls black and white, and call a network integrated if each white ball has at least as many black as white neighbors, and vice versa. Mathematically, BS, the number of black neighbors, is equal or bigger than the number of white neighbors, WS. Both networks display different colorings. Now consider the network on the left and inspect the white balls. This ball has one black neighbor and two white neighbors, thereby violating the inequality 1. Likewise, the other three white balls have more white neighbors than black. Therefore, the network on the left is not integrated. If you inspect the network on the right, you can easily verify it is an integrated network. The question is, given any network, is there a coloration that integrates it? This problem seems a difficult one, but it actually is not, as we can infer from the question, which actually is telling us one simple thing. Either there exists a coloration that integrates a network or not. How do we do to know whether this coloration exists? We obviously need evidence, a factor that we believe to be related to the property of integrated network. If we can find that out, we can structure our investigation in terms of an if-then implication and apply, for instance, a proof by contradiction. Logicians use the phrase proof by contradiction to indicate a form of proof that establishes the truth of a statement P by hypothesizing that its opposite, not P, is true, and then deriving a contradiction. To apply this method, we first have to identify an if-then implication, hypothesize that is false, and show that this leads to a contradiction, which proves that statement 1 is indeed true. What about the extreme principle? The procedure displays the same logical framework, but in the step 1, it makes use of an extreme value. Using extreme values is a tricky way of setting high standards to let emerge a contradiction. Let's apply the step number 1. We have to find a conjecture of the type if A then B. Without loss of generality, focus your attention on this integrated network. What does actually make it integrated? If you look more carefully at the network composition, being integrated might be determined by the number of polar segments, that is, those segments that link to balls of different color. How many of these segments are there? There are 7 overall. How many are there within a non-integrated network? In this case, we have 4. Since this outcome does not change irrespective of the number of balls and segments, then it is reasonable to frame our conjecture using the extreme principle idea. If the number of polar segments is maximal, then the network is integrated. Actually, I might have used infinite instead of maximal. What is important here is to point out the idea of extreme. In this case, is the number of segments, but in other problems the feature might be a volume, a surface, or any other feature. Let's move to the second step. Hypothesize the conjecture is false. When an if-then implication is false, the truth table explains that clearly. When the conditional from P to Q is false, although counterintuitive, it is false when the consequent is false too. If you find some concepts unfamiliar, don't worry, I will make another video where I will explain these things more in detail. Now, let's speak again the conjecture and hypothesize this is false. If this is false, the following statement will be true. The third step involves showing that the above statement leads to a contradiction. If you want to give it a try, pause the video and think through the statement. Can you prove why this leads to a contradiction? What kind of contradictions might one think of? For instance, we might find a circumstance conflicting against the maximality's assumption. How might we show this? Using a principle I have already shown in a previous video and that I recommend you watch, Cheryl's Birthday. This principle entails asking, given the statement, what else must be true? If the statement is true, then it would have been possible to build infinite networks and find none of them with a number of polar segments bigger than this maximal number. The second thing we can infer is its contrapositive. If the network is integrated, then the number of polar segments is not maximal, which is true because the initial statement is assumed to be true. Now, as you can see from this picture, the number of polar segments for this not integrated network is 4. How do we do to verify that 4 is actually the maximal number of polar segments while eliminating the need to make infinite computations? By inverting the colors of the balls. In other words, and without loss of generality, if we switch the black to white and the white to black, we obtain an integrated network having 4 polar segments, exactly as the not integrated one. But this contradicts the initial assumption that the number of polar segments is maximal, that is, the highest possible, or equivalently, the contrapositive we have previously identified. The contradiction stems from having assumed that if the number of polar segments is maximal, then the network is not integrated. Because this statement is false, this initial conjecture must be true. Therefore, we have found a correlation that integrates any network, and this correlation is that associated with a maximal number of polar segments.